US Physics Olympiad, year 2012, USAPHO. Semifinal exam. Problem B2. Solution for this problem you can find below this video in the description reference. For this problem, assume the existence of a hypothetical particle known as a magnetic monopole. Such particle would have a magnetic charge Qm, and in analogy to an electrically charged particle would produce a radially directed magnetic field of magnitude B equal μ0 over 4 pi multiplied by Qm over r square, and be subject to a force in the absence of electric fields F equal Qm multiplied by B. The magnetic monopole of mass m and the magnetic charge Qm is constrained to move on a vertical, non-magnetic, insulating, frictionless U-shaped track. At the bottom of the track is a wire loop whose radius B is much smaller than the width of the U of the track. The section of track near the loop can thus be approximated as a long straight line. The wire that makes up the hoop has radius A much smaller than B and the resistivity ρ. The monopole is released from rest a height h above the bottom of the track. Ignore the self-inductance of the loop and assume that the monopole passes through the loop many times before coming to a rest. Question A. Suppose the monopole is a distance x from the center of the loop. What is the magnetic flux Fb through the loop? B. Suppose in addition that the monopole is traveling at a velocity v, what is the EMF E in the loop? Question C. Find the change in the speed dv of the monopole on the trip through the loop. Question D. How many times does the monopole pass through the loop before coming to a rest? Solutions. Question A. Suppose the monopole is a distance x from the center of the loop. What is the magnetic flux Fb through the loop? First, let's draw the whole picture. This is our U-shaped track, and this is a wire loop with the radius b somewhere in the middle of this track. And let's draw the picture when this monopole is distance x from the center of this loop. On the right picture we are showing this scheme for this loop. The red line is a side view for this loop, and suppose that our magnetic charge is in point O on distance x from the center of this loop. We have to count what is magnetic flux through this loop. To count this magnetic flux, we don't need to count it exactly in the plane of this loop. We can change the shape of this surface and make it round as for this sphere, and the magnetic flux will be the same as for this plane or for this segment of this sphere. And we just need to count what is the area of this segment, because magnetic field on this sphere will be the same, and we just need to multiply magnetic field from this charge by area of this segment. And there is a well-known formula for this area. This is the magnetic flux through this area S, which is yellowish segment, and we just need to count this area, and from geometry we can say that it's equal to this expression. It's 2 pi r multiplied by height of this segment, which is r minus x. And finally, when we put it to this formula and express r through x and b, so finally magnetic flux equal this expression, where x over square root x square plus b square, that's cosine theta 0. That's the answer for question A. Question B. Suppose in addition that the monopole is traveling at a velocity v, what is the EMF E in the loop? Here we can use the change of magnetic flux with a change of this monopole position, and we count how fast is this change of this flux. First of all, EMF equal negative dFB over dt. That's expression for EMF in the loop. And now we can put expression for FB using this formula. And finally for EMF we have this expression, which we can turn to this one, mu 0 qmv over 2b multiplied by sine cube theta. That's the answer for question B. Question C. Find the change in the speed delta v on the monopole on one trip through the loop. So first let's count what is current through this loop. That's equal EMF over total resistance. Resistance equal resistivity multiplied by length of this loop and divided by cross section of this loop, which is rho 2 pi b over pi a square, and finally resistance equal resistivity multiplied by 2b over a square, and current equal this expression. After that we can count what is a magnetic field created by current in this loop in the point of magnetic monopole. There will be this expression, and we can count this integral. So this integral equal to 2 pi b sine theta over r square, or total magnetic field equal mu 0 I over 2b multiplied by sine cube theta. After that we can insert expression for current I and expression for EMF E, this one. Now we can count what is the force on this magnetic monopole. It will be Qm multiplied by magnetic field, and acceleration equal force over mass. And we have acceleration equal this expression. After that we can count what is the change of velocity. Now using expression for acceleration we can find what is the total change of speed. That will be integral from negative infinity to positive infinity from acceleration multiplied by delta t. But delta t approximately equal dx over v. We can approximately make this expression. After that express dx through theta. That will be dx over dt multiplied by d theta. This dx over d theta equal negative b over sine squared theta. And finally we have this integral, and here we can insert the expression for acceleration. Now, after cancellation b and v, we have dv equal this expression, and we have to count this integral. Let's do this. Let's count what is this integral from 0 to pi of sine power 4 theta d theta. We can represent sine power 4 theta through multiple angles. That will be this one or this one. And finally, if we take integral from this part, integral from cosines will be sines, which is 0 from 0, 0 to 0, that will give 0. And the rest we have 3 over 8, which is constant, and finally this integral equal 3 pi over 8. And we can put this result to this formula. That will be our final result for delta V. That's a negative, this expression, which is the answer for question C. Question D. How many times does the monopole pass through the loop before coming to a rest? As we can see, delta V is always negative. This is due to Lenz's law, because change of magnetic flux create the EMF, which is try to reduce this change of magnetic flux, which work against the motion. And this is always dV is negative. Number of turns could be found dividing initial speed v over dv. And initial speed we can find from energy conservation. That will be square root from 2gh multiplied by this expression and divided by this expression. That's the answer for question D.